Welcome, I'm a major from Tsinghua University. Here, we present our grammar-free DBMS fuzzing technique, which can mutate SQL test cases without its grammar knowledge. This figure shows the common DBMS fuzzer design. First, SQL mutator or generator generates new test cases continuously. Second, these test cases are sent to the database server through the database client as SQL queries. Third, the client receives the query results from the database server. Last, the checker with predefined test oracle checks the results and considers the unexecuted results as bugs. This design seems simple and intuitive. But how about the implementation in the real world? Let's see Sequencer as an example. Sequencer is a generation-based DBMS fuzzer which can detect logic bugs in DBMS. Since 2020, it has already found hundreds of bugs in various DBMSs. However, behind the large number of bugs found, Sequencer needs thousands of lines of Java code to adapt to a DBMS. For example, it used about 10,000 lines, 8,000 lines, and 2,000 lines of Java code for SQLite, Postgres, and MariaDB, respectively. So, for a DBMS developer, if he or she wants to fuzz his or her database product, he or she may just think that, oh, it seems painstaking to adapt the fuzzer to our DBMS. Shall I do it? But why are there so many lines of specialized code for each DBMS? Why is it unable to use the same code for each DBMS? The reason is the huge differences between the SQL grammars of different DBMSs. Here we show a create trigger example. We know the trigger is a common feature in DBMSs. However, the grammar of trigger creation are much different, even though in the most popular DBMSs. For SQLite, you need to use the when clause to represent the conditions of the trigger. For Postgres, you should create a function and use the execute procedure clause to target the function. While for MariaDB, you will use the if-then clause. Look at these differences in such a common feature. Considering each DBMS has their own features, I think that you can imagine how the grammar of the DBMS differs from the other ones. That's why the fuzzer needs so many lines of specialized code for each DBMS. Then we have an idea. Can we construct a grammar-free SQL mutator? If a mutator can work on mutating SQL test cases without the grammar knowledge, there is no need to write extra code for DBMS's grammar, isn't it? Without grammar SQL mutators, the DBMS developer may be nervous to write the SQL mutator or generator for the fuzzer. But with the grammar-free SQL mutator, everything seems to be simple. We only need to provide initial SQL test cases as seeds for mutation. and then everything will work. But how to construct a grammar-free SQL mutator? What is the challenge? In fact, when database server receives SQL statements, it will try to parse it to understand its semantics. If the statement contains syntactic errors or semantic errors, the server will just return error code to the client and stop the execution, which is not good for fuzzing the deep logic of DBMS. Existing solutions for syntactical correctness and semantical correctness of SQL all need the grammar knowledge, such as Squirrel, which converts SQL statements to mutable IR according to the SQL grammar of target DBMS. In fact, Squirrel also needs thousands of lines of code for each DBMS. So, without grammar knowledge, how can we generate semantically correct SQL statement? For grammar-free SQL mutator, how to find the mutable tokens in existing SQL statements, and what tokens should they be mutated into? Our solution is to make the best use of the metadata or the schema information of the DBMS. What's the metadata or schema information of DBMS? Let's look at the figure. When we create new database objects in a database, the system tables will also be inserted with corresponding items, which are automatically maintained by the server. In other words, we can know which objects are in the database currently by querying the system tables. For example, for DBMSs supporting the information schema feature, we can query the table named information schema point columns to list all existing columns and the tables they belong to. With the metadata, we can distinguish the table names, column names, trigger names, and their attributes without any extra parser for SQL. It is as if the database server already passes the SQL statements during execution, and we can directly get the server's parsing results through the schema information. So, makes the best use of the metadata. With the basic idea, we design a grammar-free fuzzing technique as follows. We named it Griffin, whose pronunciation is similar to grammar-free. It has the following steps. First, Griffin tracks the metadata of existing test cases statements as they are executed. Based on the metadata, Griffin constructs the metadata graph to describe the dependencies of metadata and statements. Second, Griffin reshuffles statements from the existing test cases, and then reconstructs the metadata graph by substituting the metadata node to correct semantic errors. The metadata graph of a test case is constructed according to the content of the test case and its metadata during execution. The topology of the graph can represent the dependencies between metadata and statements, as well as those between metadata and metadata. For example, considering we have such a test case. Create a table B, U, int primary K. Create a table A, X, int primary K, Y, int references B, U. Let us see how its metadata graph is constructed. After the first statement S1 executed, the table B and its column U will appear in the database, which can be identified through meta queries. So we can add an edge from S1 to B and an edge from S1 to U, representing that objects B and U are created by the statement S1. For the second statement S2, because of its plain text contains B and U, we can determine that its execution depends on the object B and U. So we will add the edges from B, U to S2. After its execution, the table named A and its column named XY will appear in the database. So we add the edges from S2 to A, X, and Y, and also add the edges from A to X and Y. Now, the construction of the metadata graph of the test case is finished. With the metadata graph, how does Griffin mutate the test cases? Considering we have such two test cases with their metadata graphs constructed already. First, we reshuffle the statements and get an intermediate test case, and the graph below is its current metadata graph, which is constructed according to the graphs of the two original test cases. However, the intermediate test case contains semantic errors due to no existing objects. It can also be seen in its metadata graph. From its metadata graph, we can see that the object B and U are not created by anything, just hang here. So, to correct the error, Griffin will substitute BU with AX respectively in the metadata graph, along with the token BU in the third statement replaced by A and X respectively. The choice of the substitution is following the types of the objects and the dependencies between these nodes. With these steps, Griffin mutates existing SQL test cases into a new test case with semantical correctness. We evaluate Griffin on 4 DBMSs, including SQLite, Postgres, MariaDB, and DuckDB, with comparison to 3 DBMS fathers, SQLsmith, SQLancer, and Squirrel. For the generation-based father, SQLancer and SQLsmith, we use their default fuzzing configuration. And for the mutation-based father, Squirrel and Griffin, we collected SQL test cases from the official regression test suite of the DBMSs as their initial seeds of fuzzing. The results shows that Griffin achieved highest branch coverage. For bug finding, Griffin found 55 previously unknown bugs from these 4 DBMS in total, and 13 of them are assigned with CVEs. Here is a case study, the POC of a bug in SQLite. The test case triggering the bug is mutated from 3 test cases for primary key testing in SQLite test suite. The test case is generated by the metadata guided mutation of Griffin. It needn't parse the test case or construct its AST. It's grammar-free. So, in conclusion, Griffin is a grammar-free mutation-based DBMS father. It tracks the metadata of the statements in built-in SQL test cases as they are executed, and constructs the metadata graph to describe the dependencies of metadata and statements interactively. Based on the graphs, it reshuffles statements and employs metadata-guided substitution to correct semantic errors. It outperformed other DBMS fathers in terms of branch coverage. It found 55 previously unknown bugs in total. That's all. Thank you for listening. Any questions?